So we know the tangent slope generators for sine and cosine, but we don't know the tangent slope generators for tangent, cotangent, secant, cosecant. But those are tangent slope generators that we're going to have to know. Okay, we're going to have to write equations of tangent lines to secant or tangent or any of these different functions. And I could just give it to you. However, we have all of the tools we need to discover the tangent slope generator to tangent, and for all of these, because they're all functions of our two favorite trig functions, sine and cosine. Now, if I ask you to take the derivative of sine over cosine, what would you have to use? The quotient rule, okay? This is a quotient, so make sure you use the quotient rule. We'll go ahead and do that. What would you get? Yes, let's make sure everybody can get that. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. Now, it doesn't look pretty, so let's just rewrite some stuff. Write this as cosine squared x minus a negative, so that'd be plus a positive sine squared x over, and instead of cosine of x quantity squared, I'm going to write it as cos squared x. Okay. Now, something should pop up to some of you as like, oh, can't we do this? Discuss with your neighbors what pops up. So you can't just do that. That's the first thing. You can't just get sine squared. But you could divide both of these by cosine squared if you wanted to. You got 1 plus tangent squared. That's one thing to do. Another thing to do is to realize that cosine squared plus sine squared is 1. This is the Pythagorean theorem on a unit circle. And you'll see how we will get the same exact answer here as here if I rewrite this as secant squared x. This is another Pythagorean theorem identity. So either way, we're going to get secant squared x. And it is known, and we will commit this kind of to memory, that the tangent slope generator for the function tangent is secant squared. Why don't you guys do the same thing for cotangent? Very similar to the first one. Now, if I just asked you instinctually, if the tangent slope generator for tangent is secant squared, what do you think it would be for cotangent? Probably cosecant squared, but I don't have sine squared plus cosine squared. I have negative sine squared minus cosine squared. If I factor out a -1, now I have sine squared plus cosine squared. And turns out your instincts would be almost correct. Cotangent would be negative cosecant squared. Okay? Now, let's look at secant and cosecant. We can rewrite secant as 1 over sine. Now, to find this derivative, we'd have to use the quotient rule. Sorry, 1 over cosine. So, using the quotient rule in this case, I'd have the derivative of the top times the bottom. The derivative of 1 is 0. Minus the derivative of the bottom times the top, all over the bottom squared. I'm going to skip right to that. And we end up with sine x over cos squared x. Now, that's actually a little bit too complicated to remember, and it is not what we use for the tangent slope generator of secant. So I'm going to write this out differently. I'm going to write this out kind of what I did in Unit 1, sine x over a cos x. Actually, I'm going to leave sine x. I'm going to put it over to the right, actually. I'm going to have a cosine by itself. And I'm going to have a sine x over a cos x over here. Okay, that's the same, right? As sine over cosine squared. Well, I can write this as secant x times tangent x. And that is what people know to be the tangent slope generator of secant. Why instead of sine x over cos squared x? I don't know. I feel like it's easy to remember that secant's derivative has secant in it. I don't know. That's what is like it has been established. The tangent slope generator secant and secant tangent rather than sine over cos squared. All right, do the same thing for cosecant. We probably think it is cosecant x cotangent x. Let's see if that's correct. And we would almost be correct if we made it negative cosecant over cotangent. Okay? These four needs to be added to your knowledge of the derivative of sine and cosine to your tangent slope generator kind of rule bank, where you know the power rule, you know the product and the quotient rule, you know the derivative of sine, the derivative of cosine, and you now know the derivative of all of these other trig functions. Okay, so I'll include sine and cosine just so we remember. Derivative of sine is cosine, derivative of cosine is negative sine. some things to help you remember this. Are that if your trig function starts with a C, its tangent slope generator is always negative. Okay, that's one thing. The other thing is to notice the similarities between similar looking trig functions, secants, tangent slope generators, secant tangents. Cosecants is negative cosecant cotangent. Cotangent, cosecant squared. Again, another reason I think why we use like the C's in cosecant instead of rewriting this as like the cosine over the sines is because the C's match up. This C matches up. So just make sure for next class and moving forward, these are known. And now we can, find tangent line equations to tangent. Isn't that exciting? Oh man, a tangent line equation to the function tangent. Now this isn't just tangent, this is x tangent x. Okay. Now discuss with your neighbors the derivative of x tangent x. Really quickly, like, oh, what is it? Or like, oh, don't we have to do this? Having just x to the first power trips people up. When it's x squared right here, like people are like, oh, I gotta use the product rule. All right. But then all of a sudden when it's just an x, people forget that that's still a different function and you have to use the product rule. Okay? So write a little note, and this is a good example to be thrown here. Just because it's x, that still means it's a product. Okay, so please use the product rule to find the tangent slope generator for x tangent x. Okay, I do the derivative of the first times the second plus the derivative of the second times the first, and I get this. Now, can I simplify this on the right side to be secant squared x squared? No. Okay, the x is inside the secant. I cannot multiply a value from outside of the secant to inside of the secant. It's its own function. I'd have to get rid of the function, so please don't do that. Okay, but I want an equation of a tangent line. This is how I'm going to find my slope. So let's find my slope at pi over 4. Times. Now, we should know that the tangent of pi over 4 is 1. That's the easy tangent value to remember. The other ones, like, I have to do myself. I don't have them memorized what the tangent of pi over 6 or the tangent of pi over 3 is. Okay, but pi over 4, sine over cosine, the same value. Now, the secant squared of pi over 4, this is where it's like, man, I've never had to do the secant squared of pi over 4 before. It's a little strange. But let's just walk through step by step how we can evaluate the secant squared of pi over 4. We know that secant is a reciprocal of cosine, so I can write this as 1 over cosine squared pi over 4. But we should also know that the notation of the square over the trig function is the same as if you take the trig function of the quantity all being squared. So it's actually finding the cosine of pi over 4 and then squaring it. Now I know that the cosine of pi over 4 is root 2 over 2, so I have 1 over root 2 over 2 squared. Root 2 over 2 squared is 2 over 4. Root 2 times root 2 is 2. 2 times 2 is 4. And that's just 4 over 2 times 1, which is just 2. Okay, so this turns into 2. And then if I'd like to, I can simplify the 2 times the pi over 4 to be 1 plus pi over 2. Okay, that's my slope. It's a sum of two things. You know, if I put it into my equation of my tangent line, I'd have to put it in parentheses because it's the sum of two things. If I'd like to have it as one term, which might look a little nicer, just use a common denominator, and you get 2 plus pi over 2. Okay, so here's my slope. Now I need my point. Well, y of pi over 4 is pi over 4 tangent of pi over 4, which is just pi over 4. So I have an xy that are the same. Tangent of pi over 4 is 1. Boom. Now I have my equation. Y minus y1 equals m x minus x1. This is to get us familiar with just having slopes and points that might not look nice, might not be a whole number, but be okay with it. As long as you're doing everything correctly, we're good. And I can do the same type of situation with secant at pi over 3. You're going to have to be able to find the secant of pi over 3 or pi over 4 or any value like that. So be prepared to do that. But let's move on. And let's introduce a new concept, the concept of a higher order derivative. Well, we know that if I take, say, y is equal to f of x and take the derivative of it, that the notation for the derivative, the tangent slope generator for f, is this f prime, this tick mark over the f. We know we can have the similar notation for y tick mark, y prime. But other notation that I want to make sure you're comfortable with, if you see it, is if you multiply the d by the y and multiply the dx by the 1, we could say this is dy dx. Okay? Instantaneous change in y, instantaneous change in x, change in y over change in x, slope, instantaneous change in y, instantaneous change in x, tangent slope. So, boom, notation makes sense. Well, we call this derivative, but turns out sometimes we will want to take derivatives of derivatives. Now, if I take the derivative of my first derivative, I will call this a second derivative. And now, instead of just calling this the derivative, I will call it the first derivative. I will add another tick mark to f. F double prime is what I would call this, not f two primes. And this is my second derivative. And using this notation of the dy dx, if I go ahead and kind of multiply in that d over dx, well, d times dy is d squared times y. In the denominator, dx times dx would be d squared x squared. But I could also write it as like the quantity dx squared. But since it's just notation, to keep it simple, we'll write it as dx squared. And that is my second derivative. Now, if I want to take another derivative or continue to take derivatives, we will stop using tick marks. Because after 2, it's like tough to see. And we'll just use numbers. Now, we're always using numbers on the left-hand side. But on the right-hand side, after the second, we'll use a number. So like the number 3 would represent the third derivative of f. And I can use it for any derivative, the nth derivative. Okay, if instead of 3 I have an n, it's the nth derivative. Okay? Now, what are we going to do with these derivatives? Well, we'll discover some applications of second derivatives, third derivatives. Typically, we stop at 2. Sometimes we just want to see what happens. So these first 2 situations are, hey, let's see what happens if we find the 4th derivative of sine or the 6th derivative of 2x to the 4th. Why don't you guys find the 4th derivative of sine? Now, you're probably thinking, gosh, that seems complicated. It's not. You just need to take the derivative of the derivative of the derivative of the derivative. I think that's right. Yes. You need to just take the derivative over and over and over again until you've taken the derivative 4 times. Do that. It's not complicated. There's no fancy way to get there. It's just start taking derivatives and keep going. And check your 4th derivative of sine with your neighbors, please. What's the derivative of cosine? What's the derivative of negative cosine? Yes. Yes. It'd be negative sine, which would be positive. Yep. So we get sine to cosine, cosine to negative sine, that's 2. My third would be negative cosine, and then my 4th, positive sine. The derivative of negative cosine would be positive sine. So what's the 8th derivative of sine? Sine. What's the 12th derivative of sine? Okay, so if I ask you, what is the 87th derivative of sine? You and your neighbors figure that out. So, out of the different approaches, we can go to the 84th derivative, which is a multiple of 4, which is sine, and then go 3 more derivatives. Or we can go to the 88th derivative, and we take 1 derivative less. Now, what is that like? The antiderivative? Oh, let's not talk about that until next semester. All right. And we will get... You are the best. Thank you so much. That's exciting. All right. So we get negative cosine. Now, let's find the 6th derivative of 2x to the 4th. So this is why we typically don't use this notation for y, and we use dy dx, because this looks like y cubed. So I probably should write this using dy dx, however, it's going to be a little bit more cumbersome. All right, what is the derivative of 48? 0, okay, good. The fifth. But like, man, we haven't dealt with the derivative of 0. What's the derivative of 0? 0, let's think about it graphically, conceptually, rather than a rule. Y equals 0. It's a line, right? It's a horizontal line, just like any y equals any constant. What are the slopes of any horizontal line? 0 everywhere. So the slopes of 0 are 0. So you could answer, what is the 87th derivative of 2x to the 4th? 0. Okay, good. Now, this is only true for natural powers of x, so whole number powers. It's pretty fascinating that it ends up happening like that. If there was any fractional power or any negative power, you would not get to 0. If you had a 1/2, 2x to the 1/2, what would be the negative 1/2, the negative 3/2, the negative 5/2, the negative 7/2? So like it would never get to 0. If it was a negative value, like 2x to the negative first, what would be 2x to the negative second, 2x to the negative third? Well, not 2x to the negative second, but like, so it's only for natural powers. All right. What is an application, though? That was just us doing, tricky things with derivatives. Let's look at this question. And this is one of those position kind of velocity acceleration questions. So the question is, given the position function of an object x of t equals negative t cubed plus 12t for t is greater than 0, find the acceleration of the object when the velocity first equals 0. Why would I ask this question in a section about higher order derivatives? Discuss with your neighbors, please. What?
Okay, because position to velocity.
The derivative of position is velocity, right? The derivative of velocity is acceleration, right? Rates of change of one gives us values of others. Okay, so like how quickly position's changing gives me velocity. How quickly is velocity changing gives me my acceleration, if I'm speeding up or slowing down. Well, that, my friends, is the second derivative of position. So there we go. A need for a second derivative. Now, this question is interesting. It's like two parts. It says, find the acceleration when the velocity first equals 0. So, two steps, and I would like you guys to do this problem. First, find when the velocity is equal to 0. Second, find a at that t. Go. We're only thinking about positive values for t. Now, v equals 0 is not v of 0. It's when does my velocity equal 0. So we need to take the derivative of position and set that equal to 0. When is the velocity 0? This is a quiz question. Hopefully, we did not find our velocity at 0. Rather, we tried to solve the equation. We're just going to use t equals 2. because we are told that our time is positive. Good so far? Now I need to find my acceleration at that time. How do I find my acceleration? Well, take the derivative of velocity, or the second derivative of position. And then plug in 2. Okay, I didn't give you units, so who cares? Sorry. Now the next question, hope you didn't work ahead because I'm going to change it. Gave you f double prime and asked you for f to the 4th of x. I'm going to change this from that to this. Now, please first discuss with your neighbors how you can go from f double prime to f to the 4th. What would you do? Discuss. Good. So just keep taking the derivative 2 more times. Okay. Go ahead. Derivative of secant is secant x tangent x. The derivative of tangent is secant squared. However, when I get this third derivative, secant x tangent x, and I take the derivative of it, what do I have to use? I have to use the product rule. Sometimes when things kind of aren't just like there for us, like in the initial part of the question, when like having to use a rule in a second part of a question pops up, students forget to use the rule. You got to use the product rule here. This is a common question where students will forget another situation like x tangent x. People forget, I got to use the product rule here. Here, it's like, oh, the second step, take the derivative of this, forget to use the product rule here. So we have to use the product rule. The derivative is actually pretty nasty. First, the derivative, secant, we already kind of wrote that. So write it again. So that's the derivative of secant times tangent, which is the second piece. Then I need to add the derivative of tangent times secant. You see where that comes from? Is it beautiful? No, but it's correct. This would be the second derivative of secant, or the 4th derivative. I could rewrite this as tangent squared x, kind of multiply my like trig functions, secant cubed x. Leave it like that. Fine. Okay. Cool. So be careful when we're using our rules. And once we get to the last rule on Monday for you guys, it's very important to understand we might have to do rules inside of rules and stuff like that. Moving on to not another concept, another new concept, rather a different application of the rules that we already know. So I have a table of information, and I'm asking you to find derivatives of certain things at certain values. Okay? Now, It's not that hard as long as we know that the derivative of f is f prime. And the derivative of g is g prime. Okay, right? Derivative of f plus g, f prime plus g prime. That makes sense, and that's correct. And then I just need to find this at x equals 2. Plug in 2. Then in our table, we will be able to see the information that we need. Okay, so it's not bad. F prime of 2 is 7. G prime of 2 is -4. So I get an answer of 3. Okay. Piece of cake. All right, well, let's do the second problem. All right, I say the derivative of 3f of x, g of x at x equals 4. All right, so the derivative is 3f prime of x, g prime of x. And I start plugging in 4. Wait, nope, I'm wrong. That's wrong. That's way wrong. Discuss with your neighbors. Why is that wrong? This is how they get you, okay? You think it's easy because it was easy for the first one, but then you think, oh, sure, 3f prime g prime. Like if it's not x squared cosine x, like if I gave you x squared cosine x, you'd all be like, oh yeah, product rule easily. But if I give you 3fg, all of a sudden you don't recognize that, this is a product of two different functions. So you use the product rule. Now there's two ways that we can account for like this 3. We can either bake the 3 in. I'm going to show you both. So if I bake the 3 in, make sure we understand the derivative of 3f of x is 3f prime of x, right? The 3 doesn't go away. It's the derivative of a constant times a function. That's why the derivative of 3x squared is 6x rather than 2x, Okay, so this one way would be 3f prime times g plus g prime times the first piece, which is 3f. Okay, that's one way to do it. The other way, which is my preferred way of going about these things, is if, what just happened? That's pretty crazy. Okay, we're good. The other way, my preferred way, is if we just consider the 3 as a constant and then f times g is the function. And we know the derivative of a constant times a function is the constant times the derivative of the function. Well, the derivative of this function would have to use the product rule. But instead of having it baked in, you could have it just left out. And then the derivative of f times g. Okay, and this is what I would prefer to do, is leave the constant out and then multiply by the derivative function. However, depending on the situation, sometimes I like to bake things in. When we get to implicit differentiation, I like to bake things in. Anyways, we're going to plug in 4 everywhere. Let's go ahead and do some arithmetic. So 4. We'll need all of these values. F of 4, f prime of 4, g of 4, g prime of 4. Not the prettiest. Usually they're all numbers, and when they're all numbers, you can get just one number. But in this situation, they're not all numbers. So let's see if I can do anything here. This is negative 3 pi over 2. This would be 18 pi over 2s. 15 pi over 2s times 3. 45 pi over 2s. Gross, but correct. All right. Other things we need to be careful about. So obviously, knowing our rules is important and using our rules. Questions will purposely try to trick you. This guy is purposely trying to trick you. Discuss with your neighbors why that is purposely trying to trick you.
Right. I think even though it's written like that, I think you still use.
Right, so I introduced the quotient rule with F over G, so that it's kind of similar to the product rule. They purposely know that most teachers introduce things like F over G, and they'll flip-flop it on you. So that if you write your derivative as F prime G, and I'm not going to use of X just because it'll be quicker, minus G prime F over G squared, you're wrong, okay? The derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared is not this. So please write the correct derivative. And let's plug in 9. Are they values? Change G prime of 9 to 1, please. Goodness gracious, these pies. Why? Why did I copy this down? I don't know. Okay. Go. Oops. We got 4 plus 6, that's 10 over 16, which is 5/8. Yes? Anybody else get 5/8? Yeah. Did you get 5/8? All right. All right. The one on the right involves a product rule, but also you have to still take the derivative of everything. Let's see if you guys can write the correct derivative. Don't start plugging in values yet, but let's make sure we can write the correct derivative of 3 f of x g of x minus 4 f of x. Compare your derivative with a neighbor. I don't know, for some reason, people forget to take the derivative of 4f. They don't write 4f prime because they're like focused on the product rule in the previous guy. Again, you could bake the 3 into the f and have it 3f prime and then g prime times 3f. Now go ahead and let's plug in 3, but let's change, hopefully we haven't done this already, the pi over 4 to 1. I like using ones. They make calculations easier. Okay? Oh, you already did it. Four plus 27 is 31. That is 93 minus 4 is 89. So really the last steps of finding these values, not the tricky part. Okay, the tricky part is writing the correct derivative. If we can't write the correct derivative, we have no chance of getting the correct value. But the next set of problems throw an extra little bit of trickiness in these types of problems. This is a table problem, but I'm giving you a graph rather than a table. Okay, it's similar like finding derivatives. The questions are asked a little bit differently. It's not d dx of f times g. It says, hey, p is this. Find p prime of 4. Okay, well, let's all first write down what p prime of x is. Ready, set, go. Okay, it's just the product, so just use the product rule. There's no coefficients anywhere, so we just got that. And I'm going to go ahead and write out the 4s in here. Okay, that should be straightforward. Now, giving everybody a chance to think about this, okay? I want everybody to use their brain power here, okay? Don't just spoil it for the people around you. Ask them if they know it first, okay? And then, if they don't, try to lead them in the right direction if you've already figured this out. I'm giving you a graph of f and g, but I need to find f prime of 4, g of 4, g prime of 4, f of 4. How do I get those values from this graph? Discuss. I like the thought process. I do. It's good. It's like I found the value, and then it's like the value, the derivative is 0, right? It makes sense. I like it. but it's not right, okay? But that's okay. F prime of 4. What does a derivative represent? Slope. Slope of the tangent. The important part of this is the translation of this to mean the slope of f at x equals 4. Now, if I wrote f prime of f of 4, no, then never mind. I don't want to write that. I don't want to write that. That'd be wrong. So, the slope of f at x equals 4. So at x equals 4, right here, I'm going to look at f, and I'm going to look at the slope of the tangent to f at that value. And I can see, because this is a line segment, I can calculate that slope. It's a rise over a run. I'm going down 1, right 1. That's negative 1. And to find a value like g of 4, well, g of 4 is just the y-coordinate. Most of us, we're good with that. Okay? Now go ahead and finish off the problem. And I get that. Okay, the slope of g at 4 is 0. Okay, now the last one, we have q of x is equal to f over 2g of x. Notice it's f over g. Thank you. Whoever wrote this problem is me. Find q prime of 8. Okay, well, you could either bake the 2 into the g so that you have it as the denominator, and the derivative of 2g is 2g prime. Or what could you do so that you can get that 2 out of there and worry about it later? Half. Very good, very good. Okay, so let's pull out 1/2. I feel like it's easier to work with a 1/2 out in front and worry about the other stuff later. Thought I hated Genius Hour. I love Genius Hour. I can just like slowly get through all the lesson, not having to rush anything. Make sure you guys are all good. Give you guys plenty of time to work through things so that you don't have to do much stuff at home. And I especially love the Thursday Genius Hours because it's all nice and seamless. All right, check your numerical answers with your neighbors. I don't care if you guys don't like it and you don't like being in calculus for 3 hours. I don't care. I love it. It's great. It's great for the videos. I think it's good for you guys. You guys might be like, man, can't I just like get my phone out and do some other stuff? But we're looking at 8. Whoa. Everybody else get 7/8? Did I make a mistake?
Yeah, minus.
So we're good? We're good? 7/8? G prime down 1/2. Down 1/2. Okay, so that's good. Question? We got it? What happened?
Wait, no, I have it. We're done with the lesson.
Yeah. Okay. All right. Any questions at all?